Hello, everybody. Hey, this is week 7, lecture 2, I guess. And now we are changing topics here and going into energy and work. We'll talk about that momentarily. And after this subject, we are going to finish off with momentum. And that will be the last week. And we're also going to have a midterm, which is going to be a review of everything all put together. And I will have several review sheets for you that will match up with that multiple choice midterm at the end of our 9 weeks. Okay, now the question is, what is energy? Now, everybody knows what energy is. Okay, but if you were forced to make a definition, it makes it really difficult because it has a lot of different nuances. There are many types. There are many types of energy. There's thermal energy, nuclear energy, chemical energy, electromagnetic energy, gravitational energy, light energy. Light energy, by the way, is also electromagnetic energy. Spring energy, mechanical energy, potential energy, kinetic energy. And those last three there, mechanical, kinetic, and potential, is what we're going to kind of concentrate on. But if I told you that the definition of energy from a physics point of view was the ability to do work, that probably wouldn't help you in understanding what energy is. Because what the heck is work? Now, we know that work is a lot of different things. You have to work at understanding physics or English or Spanish. You're going to have to do homework. You're going to actually do this. I have to come to work. Okay. And all of the context of which we're talking about work in that case is not work in physics. And I am going to reiterate this as we go through here, but work is equal to force times distance. And again, we're going to come back. We're going to come back to that force times distance because we need to tweak it. We need to tweak it a little bit. Okay, so anyways, let's go through a couple of examples here to see. So let's say that we have a 5-kilogram object, and we are going to have a force of 10 newtons, and we are going to go a distance of, let's say, 4 meters, and let's say that we have a coefficient of friction that is equal to 0. We're going to have a coefficient of friction that's equal to 0, which means there is no friction, okay? And we apply that to this circumstance. How much work did this force do on this object, okay? Well, we're going to just say work is equal to force times distance. Our force is 10. Our distance is 4. This would be newtons. This would be meters. And our answer would be 40. Our answer would be 40. Now, 40 what? Well, we can look here. We know that that is 40 Newton meters. 40 Newton meters. But in the same way that a Newton is a kilogram, meter per second squared, think F equals ma, mass, kilograms, acceleration, meters per second squared. We're going to have a kilogram meters per second squared times meters. That would be a kilogram meter squared per second squared. But again, we're getting more, using more words now instead of fewer. And so the unit for work and therefore energy is going to be joules. Okay, capital J. You might remember that from your days in chemistry, maybe specifically thermodynamics. Whether you had that in honors chemistry, you would have certainly had it a lot more in AP AP Chemistry if you took that class. So our answer is 40 joules. Okay, 40 joules is our answer. So now, same example here, but what if we had this force of 10 newtons and we pushed straight down? If we took that 10 newtons and we pushed straight down, would it in fact go 4 meters? Okay, and the answer is no, which probably seems pretty obvious, but there is no component. There's no component in our second example of anything that would push it or pull it to the right. Therefore, if we had 10 newtons going straight down, okay, it wouldn't do any work at all because it would not give you any distance. Okay, so we need to kind of go back here, and we need to sort of change this definition of what work is. And I want you guys to think here is if we've got a force and we've got a displacement and they're both going, if they're both going in the same direction, then we are going to have an angle of 0. We're going to have an angle of 0. And if we have a force of 10 going straight down and a displacement of 4 to the right there, that is the angle of 90 degrees. So now remember, if we have a term in from a degree point of view, okay, we're looking for a trigonometric function that if we multiplied it by sine or cosine, where if the angle was 0, it wouldn't change our answer. It would still be 40 joules. But if it was at a 90 degrees, that would give us 0. It would cancel each other out. And that trigonometric function is cosine. So think about the cosine of 0, which would be 1, and the cosine of 90, which is 0. So our new definition of what work is force times distance times the cosine of the angle. Okay, so we're going to have the cosine theta. Now remember that both force and displacement are vectors. Okay, so we're going to have the absolute value of this force and the absolute value of that force times the displacement and times that cosine of that angle, and that is going to be equal to our answer. So now, again, the absolute value of 10 going to the right is just 10, and the absolute value of 4 going to the right is 4 times the cosine of 0 degrees. It's still going to give us the same answer of 40 joules. Okay, and if we're going straight down, we're going to have 4 times. What doesn't matter? There is no displacement, but we know that it's not going to be displacement because we're going to have a cosine of 90, which is 0. So there is no work done on that object. Now let's take the sort of same example, but now, okay, now we're going to apply. We're going to apply this 10 newtons of force, but now we are making it at an angle of 60 degrees. Well, we're kind of pushing down. We're kind of pushing down on it, okay? And now we're going to have what would the work be now? So now we're going to say again 10 times 4, but now we're going to have the cosine of 60 degrees. And the cosine of 60 is 0.5. So 10 times 4 is 40 times 0.5. And now we're only going to have 20 joules of energy. And again, our coefficient of friction is 0. Okay. So now that makes complete sense. If we're pushing directly in the same direction as our displacement, we're going to get the most amount of work. And as we move that angle, up, okay, we're getting less and less work done on this object. Okay, and again, as we go up, we're pushing more and more into that surface here. Now we could do the same thing. What if our force was 10 newtons and we had 60 degrees, and we had 60 degrees that way? Okay, so again, it's going to be 4 or 10 times 4 times the cosine of 60 degrees. It's still going to be 20 joules. So we can be pushing down and we can be pulling up, and it's going to give us the same value. So really what we're looking for is what is the component? What is the component that is going in the same direction as displacement? So in this case, even though I'm saying D, we're really going horizontally. What's the component in the x direction? What is the component in the x direction of 10 if the angle is 60? Well, that is going to be this opposite side, which is going to make it cosine. And therefore, we're going to, this 10 right here is our hypotenuse, and we want this side. That would be the adjacent, and that gives us cosine. Okay, so this component right here, okay, the sine component is perpendicular to the displacement, and therefore this component does 0 work in the same way that when this 10 is going straight down, it has no component. All right, so that is one way to think, or that is kind of that definition of where we have work. I like to think when you're talking about work or energy, what are you working against? What are you working against? So essentially, you're always working against something. And if you are not working against something, then you're not doing any work. You're not transferring any energy. Another way to think about work is the transfer of energy. Okay, so if you're transferring energy from one thing to another, then you are doing work on something. Okay, so we're going to kind of take this back a little bit and see how it relates to what we've done in the past. So let's say that our initial velocity is 0, and we want to find out, hey, what was its final velocity? What was its final velocity at the end? All right, so what is our acceleration? What is our acceleration? So again, let's go back. We're going to go back and just say that this is 10 newtons, and now we're going in the same direction. We're going in the same direction as the displacement. So now we're again going back to 40 joules like we had to begin with. Now, before, if we want to figure out how fast it's going at the end, then we are going to need to know what is the acceleration. And we know that F is equal to ma, and F divided by m would equal to a. So we know that our force is 10 and our mass is 5. Therefore, our acceleration is 2. Our acceleration is 2. And we can now say that v final squared is equal to v initial squared plus 2ad for displacement. We know our initial velocity is 0, and so we're going to have 2 times 2 times 4, but then we have to take the square root of that, and our final velocity is going to be equal to 4 meters per second. 4 meters per second. All right, now, same sort of question here, but what if this is 1 kilogram? What if that is 1 kilogram instead of 5 kilograms? How much work are we now doing? Okay, we go back to our equation. Work is equal to force times distance times cosine theta, but as long as they're going in the same direction, it's just force times distance, okay? Well, notice that in here, there's no place for the mass, and therefore we're still doing 40 joules of energy. What if this is 10 kilograms? If that is 10 kilograms, it's still going to be 40 joules of work, still going to be 40 joules of work. Now, what's the difference when it comes to speed here? When it comes to speed, if we change this mass to be 1 instead of 5, okay, then we're going to have an acceleration of 10, and then we can put in 10 right there. Now we're going to have the square root of 2 times 10 times 4, which is 80. Okay, well, the square root of 80 is just going to be a little bit less than 9, because the square root of 81 is 9, so we'll call it 8.9. So obviously, if we make this 1 kilogram, and now we're going to add the same amount of energy, we're going to add the same amount of work, well, it's going to go faster. If we instead change it to 10, okay, now our acceleration is just going to be 1. And now if we put 1 in there, 2 times 1 times 4 is going to be 8. The square root of 8 is going to be something just a little bit less than 3. Call it 2.8 something. Okay, square root of 9 is 3, so this is going to be a little bit less. So we would expect, if it's heavier with the same amount of energy, it's not going to go as fast. And if it had the same amount of energy but less mass, it's going to go faster. So all of that kind of makes sense from an energy point of view. Okay, now if we change that angle, okay, then it's going to change the overall speed, because some of the energy that we are giving, that force, all of those force components are not going in the x direction. So we're only going to want the components that are in the x direction. So again, we can think of work. We can think of work as force times distance, as long as they're going in the same direction. Okay. So we might take the force and just figure out what the force is going in the same direction as the displacement, and then we just have FD. Okay, but if we take into account the angles, okay, the angle between force times distance, or with a force vector and the distance or displacement vector, then it's going to be the cosine of that. Okay, so we can think of it in different ways. All right, so again, what are we working against here? Okay, now if we change the mass, we can see that we're going to go on different speeds. And I would like us to think back to Newton's first law. And Newton's first law is often called the law of inertia. And it says an object's state of motion will remain the same unless acted on by an outside force. So we do have an outside force, and therefore we're going to change the state of the force, and we're going to speed it up. Okay, but what we are overcoming is inertia. Remember, mass is a measure of inertia, and inertia is a measurement of the object's resistance to a change in its state of motion. So a bigger object has more inertia, therefore it's going to resist that change. So one thing that energy can do is it can resist the change to its kinetic energy, or we can reduce that to the, sorry, lost my train of thought. It is going to resist the change to its inertia. Therefore, what are we working against when we have no friction? We're working against inertia. Okay, we're making it go faster. All right, so what I would like to back up here, and we're going to talk about a couple different types of energy, which you are probably familiar with, but maybe not from an equation point of view. Okay, we're going to have kinetic energy, and that is going to be either KE, or in your textbook, it's going to have an abbreviation of just K. And the definition of kinetic energy is 1/2 mv squared. So kinetic energy is the energy of movement or motion. So anytime anything is moving, then you're going to have kinetic energy. Okay? Now, we're also going to have potential energy. And that potential energy, we may abbreviate it with capital P, capital E. But in your text, the equation for potential energy is equal to U. Now, there are many types. There are many types of potential energy. For example, the energy that is stored in batteries would be potential energy, but that would be chemical potential energy. Okay, I have stored energy in my body in the form of fat, so I can convert, and this is kind of over a long term, I'm going to convert that energy of fat, which is stored in my body, into energy. I also, just the food that I'm eating, as it breaks down into glucose, and then I can then convert that glucose through cellular respiration and turn it into energy, and in the same way producing carbon dioxide and water. Think of ADP or ATP turning into ADP if you had or remember your biology. Those are all stored energy sorts of things, but we're going to concentrate on just a couple that are more from the physical point of view. One of those is going to be gravitational potential energy. If I take this pen and I lift it up, it now has more energy, because if I let it go, it's going to speed up. And if I put it up higher, it's got more energy. So when I release it, by the time it gets down, it's going to have a greater amount of kinetic energy. So that is an example of that transfer of energy. And that is really, if you think of work as the definition of a transfer of energy from one thing to another, that can kind of help you understand what work is. All right. Now, there can be another thing that is going to be stored energy, and that would be the energy stored in a spring, for example. So if I stretch it out and let it go, it's going to release that energy and go from, let's say, nothing to a certain speed. So where this is gravitational, we can have another equation, and we can have 1/2 kx squared, and that is spring energy. Now, all of these things are examples of potential energy. There's lots of other examples. We are going to essentially concentrate on these three equations. And kinetic energy plus potential energy is something called mechanical energy, and I'm going to abbreviate it with ME, mechanical energy. So what is the definition of mechanical energy? It's the kinetic energy and the potential energy of a system. And we can define system kind of however we want. So if we talk about a system of just this pen, and we move it up, we put energy into the system and we increase the potential energy, okay? And if we let go, we can transfer that energy from that system. It's going to change from potential back into kinetic, okay? Now, if we define that system as me and the pen, I lifted up, that means I did positive work, and I'll get back to this from examples. I did positive work and gravity did negative work. In our system, we didn't transfer any energy out of our system, okay? And so partly in this mechanical energy is how we define the system. But for the most part, it's going to be pretty obvious. If I sit out here and hold this pen straight out and it's not moving, okay, is there an increase? Is there an increase or a transfer of energy into this pen? And the answer is no, okay? Am I using any energy from my body physiologically? And the answer is yes, I am using energy to hold up this pen and my arm. And that does require work. It does require energy. But that was not, that may not be what the question is asking, is how much work is done on an object. So typically when we're talking about a book or a baseball or a arrow or something like that, we're really just talking about that arrow as far as the system goes. All right, so now we have mechanical energy. And now we're going to talk about one of the next concepts in this chapter, which is called the work energy theorem, okay? And that work energy theorem is work is going to equal to the change in kinetic energy. Work is equal to the change in kinetic energy, okay? And that, in turn, is going to be equal to 1/2 m times v final squared minus v initial squared. So remember, change is equal to final minus initial, okay? Now, I have not forgotten, you guys, I've not forgotten about calculus here, but since I'm thinking about it right now, we could say that work is equal to force times the change in x. And if we want to change the change in x into regular x, we can take the integral. And if you have not had calculus, again, not a big deal. But if you have x, there's something called differentiation, okay? And we talked about it a little bit in the prior chapters. So we have dx. Now, the anti-differential, okay, or if you do the opposite of differentiating, which is called anti-differentiation, well, that in calculus is known as an integral. And the integral of a differential just takes us back to what x is. Now, for those calculus people out there, you guys have not done really anything with integrals yet of any substantive amounts there, but that is coming in your next quarter. If you have not had calculus, again, you're going to be fine, because for the most part, we're essentially doing this from an algebraic and trigonometric point of view. Once we get to specific things that we're going to require calculus, I'll introduce those to you, and you'll be able to do that. Anyways, we will be back to this. Now, I want to take a look at this and apply it to our example here. So in this case, we're going to go back to our 10 newtons acting on a 5 kilogram object over a displacement of 4 meters. So we already said that we're going to end up with 40 joules, okay? 40 newton meters, same thing as 40 joules. Now, if we put in 40 joules into an object that has a mass of 5, and we have an initial velocity, of 0, then how much work, what is our final velocity? And that is where this work energy theorem makes it nice and easy. Okay, so now we can say our work is 40 joules, and that's going to equal to 1/2. Our mass is 5, and our final velocity we are looking for, but we know our initial velocity was 0, and therefore we can move this half over, and we're going to get 80, and then we're going to divide by 5, and then we're going to take the square root, and we're going to end up with V final. And we can see that 80 divided by 5 is 16, and the square root of 16 would be 4 meters per second. And that is the same thing we got when we did the example before using the kinematic relationship of V final squared is equal to V initial squared plus 2AD. So it really comes back down to the same derivations, but this is nicer in certain respects because we do not have to calculate. We do not have to calculate the acceleration that we did right there. Okay, we do not have to calculate the acceleration right there. Now, if we put in 1 here, okay, then we're going to again get the square root of 80, which is what we got before, which was just a little bit less than 9. If we put in 10 there, then we're going to get the square root of 8, which is going to be a little bit less than 3, because the square root of 9 is 3. So we're getting the same answers as we did there, but very often this work energy theorem works out to be very nice. Okay, so we're going to come back to this. We're going to come back to this in a second, and we'll get rid of this, and we will get rid of this. All right, and now we are now going to say that we're going to have a coefficient of friction. We're going to have a coefficient of friction of 0.2. And again, this time we're going to have an initial velocity of 1 meter per second. And we're going to have a final velocity. We're going to have a final velocity of 1 meter per second. So we did not change speeds. We did not change speeds, okay? But now let's talk about the work that we have to do, okay? And again, here's a question. What are we working against? Well, now we have some resistant force, and that resistant force is going to be equal to the force of friction. And a reminder, the force of friction is equal to mu force normal, okay? And that is going to be equal to 0.2 our coefficient of friction. Now remember, our normal force is going to be the opposite, in this case, the opposite of the gravity because it's horizontal. So gravity going down is going to be 5 times 9.8. Now, to make this a little bit of a simpler example, I'm going to call that 9.810, right? So we're going to have the weight is 50 newtons down, and therefore the normal force is 50 newtons up. 50 down, 50 up. So now we're going to say, our force of friction is 0.2 times 50, which is going to be 10 newtons. Okay, so we're going to have a force of friction of 10 newtons. So what are we working against? We're working against friction, okay? So again, we're still going to do 40 joules, but how much work did friction do? Okay, well, friction has a force of 10 and it's got a displacement of 4. So 4 times 10 is 40. So friction did 40 joules of work, or did it? And the answer is it did negative 40 joules of work, because friction is working in the opposite direction of displacement, okay? Therefore, the angle between them is 180. And if we use the definition of work is equal to force times distance times the cosine of the angle, we're going to end up with negative 40. Okay, so that's one way to think about it. The other way to think about it, we just know that force is going that way and the displacement is going that way. So we know that this force is negative. So negative 10 times 4 is negative 40. Okay, so friction did negative 40. We did positive 40. So if we look at the net force was 0, positive 40, negative 40. We go back to the work energy theorem. Well, the velocity stayed the same. So we didn't do any work. We didn't do any work to the system because the system was that object and friction and the surface. Okay. Now, you got to be careful because even though there was no net force done, okay, we did 40 joules. We did 40 joules of work on the object. Okay. And friction did negative 40. So when we add those together, the net force is 40. So when you're looking at a problem, you got to think about what is the difference, or you got to read the question particularly, because they might say how much work was done on the object. And then it might also say how much work was done by friction. So you got to pay attention to those things and answer them respectively. But even though we have this, even though it did not change velocity, we still ended up with this work energy theorem still being valid. So what if we now said this initial velocity, that initial velocity was 0, okay, and we don't know what the final velocity is. Well, now when we add up all of those forces, what are the sum of the forces? Well, we had positive 10 this way, which is our applied force. We had negative 10, which is our frictional force. There would not be any net force greater than 0, so it wouldn't move. So it wouldn't move. We're not going to do any work. Now, before, okay, it was already going. And if it's already going and we don't have any outside force, it's going to continue to go at 1. Now, if we think and combine our last two ideas, so instead of saying that it's 10 newtons, we're going to say that it's 20 newtons, okay? Now, if we think about this in terms of what we are working against, what are we working against? So in the first case, okay, we were working against inertia. And in the second case, we were working against friction. So if we're going to work against friction, we will have done, okay, negative 40, okay? And if we think about 20, our applied force is 20, and we move that for 4 meters, then that's going to be 80 joules, okay? So we're going to put in 80 joules, okay? And then we're going to have 40 joules got used up. 40 joules got used up by friction, okay? That means we have 40 joules left over, okay? Well, what are we going to use? What are we going to use that leftover energy? What are we now working against? And now we're working against inertia, and we're going to make it go faster. And as we saw from our previous example, if it was 5 kilograms, at the end of those 4 meters, it's going to end up going 4 meters per second. That's square root of 16 that we had talked about in a couple of different results. So the amount of work that we put in can be divvied up into different things. It could be working against friction, and it could also be working against inertia. We could also be working against a spring, okay? And we could also work against gravity. And that's what our example is going to be next, okay? So let me let me talk about gravity. I've got a little more space here. So now, if I take this and I am going to move it up, let's make this a book. Okay. Okay, so we have our physics book right here. And again, we have a physics book right here. Now let's just say that this is 1 kilogram. This is 1 kilogram. And I am going to start here. We'll start right here. And then we're going to start right here, and we're going to lift it up there, 1 meter. So if this is 1 kilogram and we move it 1 meter, how much work, okay? So this is going to be 1 meter. How much work did we do? How much work did we do? Well, work is going to be force times distance, okay? Well, what force are we overcoming, okay? So we're gonna have an applied force. Sorry about that. That was the Scatterbell song. All right, so back to where were we? So if we push this book straight up 1 meter, what are we working against? Well, we know that mg, we're going to have the force of gravity going straight down. So now watch this. If we have an initial velocity of 0 and we have a final velocity of 0, okay? Now, in order for that to take place, okay, obviously if I want to get it from here to here, I have to be more than 0, right? So I'm going to get it going, and then I'm going to be going at a constant velocity, and then I'm going to stop it at the very end. So if we're just thinking about moving it up at a constant velocity, this will be the same thing. Okay, so the sum of our forces has to equal 0 if we're moving at a constant velocity. Therefore, Fa is equal to mg, okay? And now we're going to multiply that by our distance, which is 1. They're both going in the same direction. So the angle between them is 0. And so this is going to be mg, okay, is our applied force. And instead of distance, we're going to have height, okay, same thing. And in this case, we're going to have 1 times 9.8. Okay, times a distance of 1 meter, meters per second squared, kilogram, meter squared per second squared, that is joules. We're going to say 9.8 joules. That's how much work we did. If we go back to the work energy theorem, that 9.8 should equal to 1/2 of 1 times v final squared, and that would be the square root of 19.6. The square root of 19.6 is 4.42. But didn't I say that it ended at 0, started at 0? Okay, and that's because there was something that did negative work. And the stuff that did negative work was, in fact, gravity. So now we've got gravity, this mg that's going down, okay? And it went up 1 meter. They're going in opposite directions. So that's a cosine of 180. Or we can just think of 1 is positive and 1 is negative. And now we're going to end up with negative 9.8. 9.8 minus 9.8 is 0. So that should not speed up. Okay, now again, this can be essentially very confusing, particularly how can you go from 0 to 0? Okay, now in the beginning, I've obviously have to give it some work, some extra energy to get it going. Once I get that extra energy, now I'm only working against gravity. But at the very end, right before it stops, it's essentially, I don't have to work as hard, and I'm kind of letting it coast. I'm letting it coast until it stops. So that extra energy here is made up for the less energy up there of it coasting. So we can still think of it as starting at 0 and ending at 0. And it doesn't really matter how fast or slow it's going in the middle. If it starts at 0 and ends at 0, there is still going to be no net work acting on the object. But I can still say I did positive 9.8 joules of work. Gravity did negative 9.8. So now if I'm moving it down, okay, I'm now doing negative work because my force is still up, but my displacement is down. So now I did negative 9.8 joules to bring it back, where gravity is going 9.8, and the displacement is in the same direction, cosine of 0, and therefore, in that case, gravity does positive, okay? Now, if I give it more than 9.8, okay, then it is going, by the time it starts at the bottom and gets to the top, it will be going faster. It will be going faster than 0 because that extra work will translate into that change in kinetic energy, that translate into that extra kinetic energy. Okay, same thing happens when we're talking about friction. Friction is going to do negative work, and my applied forces does positive work, and therefore we can still add up to 0, not speed up, even though there is energy involved. It has to do with the energy to the system. All right, so we can put in energy. We could be going overcome friction. So we could have a situation, okay, where we're going to end up having a spring that is attached to a mass over a rough surface. And the question might ask, how much energy does it take to move this block from here to here? What are we working against? Okay, and we start out at, let's say, 0, and we end up going at 2 meters per second. Okay, so what are we working against? Well, in this case, we're working against the spring. We're working against friction. We're working against the height, and we're also working against inertia. So in this case, we would essentially have 1, 2, 3, 4 different equations to calculate how much work it took to bring it from here to here, from 0 to 2. And all those things we will be exploring. Okay, there is going to be one section in the book, and I think it is the second section in chapter 7, and which is a scalar product, and I'm going to kind of transfer us over here. Okay, now. This is also known as a dot product, okay? And a dot product, and this is not just useful. It is not just useful in physics, but there are many applications. For example, in linear algebra, which has to do with other things. But vector A dot vector B, vector A dot vector B is the dot product, and that is equal to the absolute value of A times the absolute value of B times the cosine of the angle between them. So why is that important? It's because we have the same thing. What we have done here is force vector times the displacement vector is equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. And that's where we're going to give an answer. So for example, previously we talked about a 10 Newton force in the I direction and a 4 meter displacement also in the I direction. Okay, that's going to be 4 times 10. Well, if they were both going in the same direction, that would be cosine of 0. Cosine of 0 is 1. And we would end up with 40 joules, like we had in our previous example. If we're talking about the frictional part, then it's going to be 180 degrees, and therefore we're going to get negative. So there is going to be a couple problems I'm going to give you in the problem set starting on Monday that's going to deal more specifically with this. And I will address them in the help, but it is in section 7.3, and that is the dot product. As we move on into other things, primarily angular velocity and angular momentum, torque, and things like that, there is also something called the cross product. And the cross product is going to be F cross B, and it's going to be the absolute value of A times the absolute value B times the sine of the angle instead of the cosine of the angle. This is sometimes called a scalar product because energy is a scalar. It does not have direction. And when we get to a cross product, that is going to be a vector product because the answer is also going to have a direction, which we will talk about in the next quarter when we come back in the spring. All right, so you guys, that is the overall. I'm going to give you a couple questions dealing with the examples that we did for our question of the day for Friday. Okay, thanks guys, and we will see you on the next video.